All right, so let's look at what happens if you have a force that varies. So if it varies by position, then if we're moving from some point A to some point B, we're going to take all of these little essentially slices of work, right? We can take that force, right? This is the force, of course. um, and all these little distances, right? And we can add them all up to get the total work done. So we just integrate the force with respect to x to get the total work done. So let's see how that works. So in example 2, we've got a spring, all right, and the spring has a force that varies by the position. So the more you compress it, the more force it pushes back. So it's pretty easy to compress at first, and then it linearly gets more difficult to compress. And the function of force needed to compress the spring is essentially just 5x, right? And we're asked to find the work done to compress the spring from 0 centimeters to 20 centimeters. All right, so this is pretty straightforward, but be careful. All right, so notice the force is in newtons. All right, and a newton is a kilogram meters per second squared. So if we want our units to be consistent, and we're given x values in centimeters. All right, we don't want x values in centimeters. We want them to be in meters so that they are consistent with the units of a newton. So be careful and watch your units. So we have to convert these x values. So of course 0 centimeters is 0 meters, and 20 centimeters is, we're just going to divide by 100, so we get 0.2 meters. Okay, so when we integrate the force, so we're going to get the work. So work is equal to the integral from 0 to 0.2 of the force 5x through some infinitesimal distance dx. All right, so now that we have it set up, it's pretty straightforward. When we integrate 5x, we get 5 halves x squared. And we're going to evaluate that from 0 to 0.2, which gives us 5 halves times 0.04 minus 0, which is essentially 0.1, and the units now are in joules. All right. All right, so it takes 1/10 of a joule to move that first 20 centimeters. And in part B, we're asked to find the amount of work done to move the next 20 centimeters. Well, I guess it's not the next, is it? We're going from 10 to 30. Okay, so it's another 20 centimeters, but in a different range of distance. So the work is just again going to be the integral, but we have to convert these to meters. So this is going to be 0.1 meters and 0.3 meters. Okay, so watch your units. That's important. All right, the work is equal to the integral from 0.1 to 0.3 of the same 5x dx. All right, so again, we have 5 halves x squared evaluated from 0.1 to 0.3. So we get 5 halves times 0.9. Whoops, not 0.9. It's 0.09, right? Because that's 0.3 squared. 3/10 times 3/10 is 9/100ths. And when we square 0.1, we get 0.01. Okay, so if you evaluate that, you get 0.2 joules. Okay, so you notice how we're moving 20 centimeters in both of these cases, but because of the fact that the force increases with distance, right? We have this force that looks like, I could graph it, it looks like 5x, right? So initially it doesn't take hardly anything to compress the spring, but as you compress it more and more, it gets harder and harder to compress. So it's going to take more work when the spring is already compressed a little bit than when it's just starting out at its natural position. So a couple things to be aware of when you're doing these problems is that you've got to watch your units. All right. Now I'm going to write this down here just so you have it. A Newton is a kilogram meter per second squared. So if you're working with newtons, you want everything to be in kilograms, meters, and seconds. All right. And a joule is a Newton meter, right? Newton meter. And again, you've got to have everything in terms of kilogram, meters, and seconds. So a joule is a kilogram meter squared per second squared. Okay. So it's very important to watch your units when you're doing these problems.